Coulomb's law are going to be the topic of this lesson in my new general physics playlist, which when complete will cover a full year of university algebra-based physics. Now, Coulomb's law provides for us the formula for the force between 2-point charges, and we call this the electrostatic force. It's one of the 4 fundamental forces, and this is the first place we're encountering it. And we're going to learn how to treat it as just one other force to add into our growing repertoire of forces that we can apply to mechanics problems, both in 1 dimension and 2 dimensions. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. So let's dive right into Coulomb's law here. So F equals K Q1 Q2 over R squared. So K is the Coulomb constant, and it has a value of 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. So notice we have the absolute value of Q1 and the absolute value of Q2. Those are the magnitudes of the charges that are either going to be attracted to each other or repelling each other. And then all over the distance of separation squared. So we kind of got this diagrammed here. So I've got 2 charges, Q1 and Q2. They could both be positive, they could both be negative, or one could be positive and one could be negative. Now we know that like charges repel, so if they're both positive or both negative, that's going to be a repulsive force away from each other. But if one's positive, one's negative, we know that unlike charges or opposite charges attract, so it would be an attractive force pulling towards each other. All right, so one thing to note, not everybody puts the absolute value brackets on this, and they teach that if you plug in Q1 and Q2 and they're both positive or both negative, that overall the force would come out to be a positive number. And in such cases, they tell you that you should know that that's a repulsive force. Whereas if one of these was positive and one of these was negative, then it would come out to be an overall negative number. And you should know that when you plug in your Q1 and Q2 without absolute values and you get an overall negative number for the electrostatic force, that is a repulsive force. Now, I'm not going to teach it that way. I'm just going to assume that you know that like charges repel and unlike or opposite charges attract. So we'll leave it at that. Now, one thing you should note here, so this is very similar to what we saw with the universal formula for gravity. So I'm going to compare it to gravity a couple different times in this chapter and the next. So if you notice, we had F equals G m1 m2 over r squared. Now with gravity, this was the attractive force between objects that have mass. Whereas for our electrostatic force here with Coulomb's law, this is the either attractive or repulsive force for between objects that have charge instead. Now notice there's only one kind of mass, and so we only ever dealt with gravity being an attractive force. It was never repulsive. But because there's 2 different types of charges in the universe, it turns out, one we call positive, one we call negative, it turns out there's 2 different possible forces, one attractive, one repulsive, and that's going to be one key difference. So, and I'll point that out a little bit later. So, but you're used to seeing gravity quite a bit, but seeing, electrons, following a force and things of the sort may not be the most common thing to you. So when applicable, I will relate oftentimes this electrostatic force back to gravity in a couple key places, noting one key difference with the possibility of either attractive or repulsive forces. All right, so a couple key things to see here. So if you look, we can see that this electrostatic force is proportional to the magnitude of Q1. That electrostatic force is proportional to the magnitude of Q2. If I double the magnitude of Q1, the overall electrostatic force is going to double. If I double the magnitude of Q2, the overall force between the two again would double. And if I double the magnitude of both charges, then the overall force between them is going to quadruple. Now, similar fashion, so that force is inversely proportional to the distance of separation squared. So if I double the distance between these 2 charges, so the overall force is not going to go down by a factor of 2, but by a factor of 2 squared, by a factor of 4 instead. And again, that's similar to what we saw with gravity, another one of our inverse square laws. And from here, we're ready to dive in to do some plug-in and chug-in. So in this diagram we've got up here is as good as any. So let's take a look at the first question on here and try to make the numbers nice where possible, but we will need your calculator a little bit in this lesson. So first question here says 2-point charges, each of magnitude positive 1.0 coulombs, are 0.1 meters apart. What is the magnitude of the force experienced by either one of the charges? So here we've got positive 1.0 coulombs, and here positive 1.0 coulombs, and here we've got a distance of separation of 0.10 meters. All right, so not so bad to calculate here. So just do some plugging and chugging. F equals K, again, times the magnitude of Q1 times the magnitude of Q2, all over R squared. K is 8.99 times 10 to the ninth. And again, that's Newton meters squared per Coulomb squared. You can see how the math is going to work out here, or at least how the units are going to work out. So once we multiply Q1 and Q2, the coulombs will end up canceling, or at least the Coulomb squared in this case will cancel. And these were both 1 Coulomb. So times 1.0 coulombs times 1.0 coulombs, and then all over the distance of separation squared in SI units of meters, so 0.01 meters. And don't forget to square it. And this we can do in our head. And I chose some nice numbers here. We're going to find out that, 1 Coulomb is actually a fairly significant amount of charge. In fact, it's a ginormous amount of charge. So, but it makes the math nice for this first example. And in this case, so 8.99 times 10 to the ninth times 1 is still 8.99 times 10 to the ninth. And dividing by 0.1 is the same thing as multiplying by 10. So dividing by 0.1 squared is the same thing as multiplying by 10 squared, or multiplying by 100. And so we can do this one in our head. And in this case, it's just going to be 8.99 times 10 to the 7th. And if you look here, the meters squared cancel, the coulombs squared cancel, and you're just left with an answer in newtons, as it should be. So 8.99 times 10 to the 7th newtons. Now again, 1 Coulomb is a phenomenal amount of charge, and you're not likely to actually encounter a problem with actual point charges having a value of 1.0 coulombs. That's actually pretty ridiculous. So we're going to redo this problem, revising the numbers just a little bit to resemble something you're a little more likely to see. All right. So swapping these out a little bit. So 2 point charges, each of magnitude 1.0 microcoulombs. So we'll switch this out to microcoulombs, are 0.1 meters apart. So we'll leave that alone. What is the magnitude of the force experienced by either of the point charges? And so in this case, where this is going to change this just a little bit, instead of 1 Coulomb here, so we can't plug in microcoulombs. We've got to put this still in coulombs, but 1 microcoulomb is 1 times 10 to the negative 6 coulombs. So I'll change our calculation now. Again, technically, you could probably still do this in your head. So 8.99 times 10 to the ninth times 1 times 10 to the minus 6 would be 8.99 times 10 to the third, times an additional 1 times 10 to the negative 6 would be 8.99 times 10 to the negative third. And then again, dividing by 0.1 squared is the same thing as multiplying by 10 squared. So multiplying by 100, which is going to get you 8.99 times 10 to the negative 1 newtons now, or just simply 0.899 newtons. Cool, so I just wanted you to see this both kind of in a simpler fashion where the math was going to be just a teeny bit easier. So the truth is, you can still do this in your head, but these are now with microcoulombs or nanocoulombs or picocoulombs. Those are going to be magnitudes of charges you're much more likely to encounter in a problem you're likely to see. So the next application of Coulomb's law here is going to end up being a two-dimensional problem, and we've got 2 different point charges acting on a third point charge, and to find the resultant force, we've got to find the resultant vector. We'll be adding those together as vectors. All right, so the question says, what is the magnitude and direction of the net electrostatic force experienced by the positive 2.0 microcoulomb charge in the following diagram? And the diagram is definitely included on the study guide as part of the question here. So this is part of the problem. In this case, we can draw a really quick free body diagram here for the positive 2.0 microcoulomb charge. And it's experiencing a force due to this negative 1 microcoulomb charge. And because the charge of interest is positive and this other one is negative, they are unlike or opposite charges, and there's attractive force between them. And so for the 2 microcoulomb charge, that's going to point to the right. Now, if we cared for the negative 1 microcoulomb charge, that would be a force directed to the left. So when you do Coulomb's law, you're actually calculating the magnitude of the force experienced by either of the point charges. So, but they will be equal in magnitude, opposite in direction to satisfy Newton's third law. And so in this case, again, for the positive charge, it's directed to the right, but for this negative charge, it would be directed to the left if we cared. All right, now our positive 2 microcoulomb point charge is also feeling a force due to this positive 4.0 microcoulomb point charge, and they are like charges, so it's going to be a repulsive force. And so for the 2 microcoulomb charge, that's going to be directed up. And again, if we cared for the positive 4.0 microcoulomb charge, that would be directed down. Again, equal in magnitude, opposite in direction. And so we can see there's really 2 forces acting on our positive 2.0 microcoulomb charge, and the resultant vector, in adding them in tail fashion, is going to be somewhere in between, so up here in the first quadrant, if you will. All right, so but we definitely have to add these as vectors, so we're going to calculate the force using Coulomb's law for both, and then add up the resultant vector. All right, so let's start with the x direction here. And so in this case, your force is going to be kqq over r squared, so 8.99 times 10 to the ninth Newton meters squared per Coulomb squared, times q, and we got 2 times 10 to the minus 6 coulombs. So, and 1 times 10 to the minus 6 coulombs. And notice, because I know we're plugging in absolute values, I didn't bother to carry the negative sign through. It's going to go away anyways, and we already figured out that it's directed to the right based on the fact that opposite charges attract. All right, and then all over the distance of separation squared, and 1 micron is 1 times 10 to the negative 6 meters. And definitely don't forget to square it, one of the more common mistakes to make. Now, this is probably one you could do in your head, but you can definitely let your calculator do the work for you as well. But you might see that this 10 to the minus 6 squared could cancel out both of these 10 to the minus 6s, and you're really just left with 8.99 times 10 to the ninth times 2, and really times 1, but anything times 1 is itself. So that's ultimately what this is going to come down to. So 8.99 times 10 to the ninth times 2e to the negative 6 times 1e to the negative 6, and divided by 1e to the negative 6 squared. Don't forget to square that. And it comes out to, just as if we'd multiplied 8.99 times 10 to the ninth times 2, it comes out to 1.798 times 10 to the 10th. I'll write that over here, actually. All right, that is a rather large number. All right, let's move on here and now find the force between the positive 2 microcoulomb and positive 4 microcoulomb charge. Set up Coulomb's law once again. 8.99 times 10 to the ninth Newton meters squared per Coulomb squared times 2 times 10 to the negative 6 coulombs times 4 times 10 to the negative 6 coulombs. And once again, all over 1 micron, micrometer, micrometer, however you want to say it. 1 times 10 to the negative 6 meters. And once again, do not forget to square that number. And similar to the last one, you're ultimately going to end up with 8.99 times 10 to the ninth times 2 times 4, because the 10 to the negative 6 parts will cancel, but by all means, let your calculator do the math. And for me, I'm actually just going to put in the last answer I just stuck in and just change some numbers here. I'm going to change the 2 times 10 to the negative, no, actually, I'm not going to change that one, leave that one alone, but I'll change the 1 times 10 to the negative 6 we had in before and make that 4 times 10 to the negative 6. So you can, if you don't know how to use your TI calculator, if you're using one, you can use the second function enter to put in the last entry, which is just what I did there. So, and from here, oop, I put the 4 in the wrong place. Let's get that in the right place. So the 4 goes there. The denominator is still 1 times 10 to the negative 6 squared, and we're going to get 7.192 times 10 to the something newtons, and I got to count some zeros here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Still times 10 to the 10th, because 9 times 8 still would have been, yep, times 10 to the 10th. 72 times 10 to the 10th, or 10 to the 9th, which is 7.192 times 10 to the 10th newtons in this case. And again, just as a reminder, this is in the positive x direction, this is in the positive y direction, which makes it convenient. So normally, if these weren't purely in the x or purely in the y, we'd have to break them up into components using sines and cosines. So but in this case, this is all x, this is all y, and we can go straight to our Pythagorean theorem to get the magnitude of the resultant vector. And so in this case, we're going to have 1.798 times 10 to the 10th squared plus 7.192 times 10 to the 10th squared. We'll take the square root to get the result, the magnitude of the resultant vector here in this case. And so again, 1.798 times 10 to the 10th squared plus 7.192 times 10 to the 10th squared equals, and then square root of that answer, we're going to get 7.41. In fact, I want to round this to 2 sig figs, so just 7.4 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 still. So 7.4 times 10 to the 10th. Newtons. Now that's our magnitude of our force. Now we still need a direction. And you might recall that tangent theta is going to equal the y component over the x component. Which in this case, that y component was again the 7.192 times 10 to the 10th over the 1.798 times 10 to the 10th. And we'll take the inverse tangent to get the angle. All right, so 7.192 times 10 to the 10th. And if you realize it, you could just drop the 10 to the 10th part, but I'll just keep it in. So divided by 1.798 times 10 to the 10th equals, and then I'll take the inverse tangent of that last answer. So by the way, this came out to exactly 4, and then taking the inverse tangent is going to get us 75.96 degrees, which I'll just round to 76 degrees. So, cool, and that makes sense. So we figured it should be bigger than 45 degrees since the force due to the 4 microcoulomb charge is going to be bigger than the force due to the -1 microcoulomb charge. And so it should be pointing more in the y direction, less in the x direction. Definitely should have been an angle bigger than 45 degrees, obviously still less than 90. So, but there's your answer. So force is 7.4 times 10 to the 10th newtons at an angle of 76 degrees. So this last question is also going to be a two-dimensional question, but it's going to be a two-dimensional mechanics question. So we're going to draw a free body diagram. We're going to do sum of the forces, or net force in the x direction, net force in the y direction, and then solve that system of equations. So the question says, two small metallic spheres, each of mass 1.0 grams, are suspended by very light strings, i.e. strings that are effectively massless, from a common point as shown in the following figure. The spheres are given the same electric charge, and it is found that they come to equilibrium when each string is at an angle of 30.0 degrees with the vertical. If each string is 10.0 centimeters long, what is the magnitude of the charge on each sphere? So because these two spheres have exactly the same charge, either both positive or both negative, it's going to be a repulsive force, and so they're pushing each other apart. And it turns out they come to equilibrium when the angle with the vertical on either side here equals 30.0 degrees. So we're going to set up free body diagram, set up again some of the equations or some of the forces, net force equations, and then solve the system until we can ultimately solve for Q here. Now when we set up Coulomb's law, we usually have Q1, Q2, but because these have exactly the same magnitude of charge, I'm just going to generically use Q, which makes this just a little bit easier problem. So, all right, let's start with a free body diagram here. We can choose for either one of these since they're identical. And I'll do the one on the left here. And so in this case, we have the weight pointing down, and that's mg. We have a tension pointing up the string here, I'll call T, and then a repulsive force pointing to the left away from the other charge, which would be K Q squared over R squared, the Coulombic force. All right, so we can definitely see this is a two-dimensional problem. So we've got components of different forces in the x and y directions. So we'll have to break this up a little bit. And so we'll have the sum of the forces in the x direction. And in this case, in the x direction, we've got a component of tension and then the Coulombic force. The component of tension is going to point in the positive x direction. And in this case, that component's going to be T. And in this case, if we kind of finish the right triangle here, so if this angle up top is 30 degrees, then this angle down here is going to be 60 degrees right here. And that's typically the angle with respect to the x-axis that we use. And so in this case, the component of the tension that points in the positive x direction is T cosine, the adjacent side here, 60. So T cosine 60 degrees. And pointing the opposite direction, in the negative x direction, is the Coulombic, so minus K Q squared over R squared. And again, we're in equilibrium, so that adds up to 0. And then the y direction, sum of the forces. In this case, once again, in the positive y direction, we've got a component of tension. And that's going to be T sine of 60 degrees. So, and then pointing downward is the weight, so minus mg. And once again, we're in equilibrium, so that adds up to 0. There's our two equations, and ultimately, we're going to want to solve for Q. Now, a couple things. We don't have the distance of separation just yet, but we can figure it out. And so one, we know the length of these strings is 10.0 centimeters. And so we look at our right triangle. This is adjacent to the 60-degree angle. That's the hypotenuse for 10 centimeters. So this is going to equal 10 centimeters times cosine of 60 degrees, or sine of 30 degrees if you want to look at the opposite, the 30-degree side. Either way, whether we use cosine of 60 or sine of 30, it's equal to 1/2, and 10 times 1/2 is 5 centimeters. And so you've got 5 centimeters here, but you're going to have an additional 5 centimeters right here. And so the distance of separation is just 10 centimeters. Just makes the math a little bit easier here, and setting up the equation is just a little bit easier as well. So we do know the distance of separation here. So, but to solve for Q, it would mean we also have to know the tension, which we don't yet know. So, but we'll use the other one to solve for tension here. So in this case, we'll have tension times sine of 60 degrees is going to equal mg. So, or tension is going to equal mg over the sine of 60 degrees. Now we can do some plugging and chugging here. So tension is going to equal our mass, which again was 1 gram, but this has got to be in kilograms. So that's 1 times 10 to the negative 3 kilograms times 9.8 meters per second squared, all over the sine of 60 degrees. Let's get that tension. Let our calculator do the heavy lifting for us. All right, so 1 times 10 to the negative 3 times 9.8 divided by the sine of 60 gets us 0.0113 newtons. All right, so there's our tension, and we can take that tension and plug it right back in here, so to solve for Q. And so I'll rearrange this just a little bit for just a second. We've got T cosine of 60 degrees. It's going to equal, I'll add this to the other side, K Q squared over R squared. T cosine 60 degrees times R squared over K. It's going to equal Q squared, and then we'll take the square root of both sides and be done. All right, so that tension was again 0.0113 newtons times cosine of 60, which happens again to equal 1/2, times the distance of separation squared, and 10 centimeters is 0.1 meters. Don't forget to square it. And then all over K, 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. Cool, and then we'll take the square root to get Q here. Cool, and we could have done this in steps, but sometimes it's convenient just to kind of solve for your variable before you plug all the numbers in, like so. So in this case, 0.0113, and it's the last answer of my calculator, I'll kind of leave that there, times the cosine of 60 times 0.1 squared and divided by 8.99 times 10 to the 9th. And that's going to get me 6.29 times 10 to the minus 15. We'll take the square root of that and get 7.93 times 10 to the minus 8. And in the end, we're going to want, looks like 2 sig figs. So I'll round that to 7.9 times 10 to the minus 8 coulombs. Cool. You could also look at this as being equal to 79 nanocoulombs as well, or 79 times 10 to the minus 9 coulombs. If you're taking a multiple choice test, you might see it represented either way. The only point I bring that up, it's not uncommon to see charges again expressed either in microcoulombs or nanocoulombs or picocoulombs, whichever happens to be kind of nearby and most convenient. If you found this lesson helpful, consider giving it a like. Happy studying.